I'm going to start number 3. We've got this traffic light, suspend 2 cables, find the tension in each cable. Alrighty. So I captured that so that I didn't have to redraw it. So this is problem number 3 here. And the first thing I'm going to do is my force diagram. My force diagram, I would have a force of tension 1 here, a force of tension 2 here, and I'd have the weight of the traffic light down like that. So that would be what I was looking for the Y for this, for the not the free body, but the force diagram, showing the situation and all the forces on it. Isaac. Right, for this one, I could also do like a tension in here if I want to, but I'm kind of considering that this whole thing is I'm just trying to get most of the forces on it. If I was to put a tension in here, I might put a tension down and a tension up like that, but they're really kind of inside the whole situation. Let me draw the free body and you'll see why I'm just going to go with the blue ones to simplify. You could have also pictured this as the traffic light attached directly to those 2 ropes. Yeah, and it would actually be transferred up there through this tension. And that's why I think sometimes the free body, remember, the free body is our way of more simplifying it so that we can just focus in on the forces, which would give us this. FT2, the weight FG, and FT1. That's exactly what you should have for your free body. And that's where the force diagram can be either less confusing or more confusing than the free body sometimes. And of course, my next step is going to be I want to break this free body into X and Y, but to do that I need to break these into their components. So if I have FT1 pointing in this direction and FT2 pointing in that direction, I want to break them into what are their components horizontally and vertically. And I'm told, that angle up there at the top is 60 on the left and 30 on the right, which means that this angle is 60 here, and this angle is 30 here. Alright? So, horizontally, like we were doing the other day, I have FT1 cosine 60 degrees, and FT2 cosine 30 degrees. Should look very familiar from our last class. And then for the vertical parts, they're opposite, so they're going to be sine. So I have FT2 sine 30 degrees. Whoops, I forgot my degree symbol here. And I have FT1 sine 60 degrees. Alright, so I've broken that into X and Y, and now I just need to record that down here. Try to zoom down a little bit. And so horizontally, I have 2 forces. Of course, my acceleration in all of these cases is 0. This way I've got ft1 cosine 60 degrees. This way I've got ft2 cosine 30 degrees. That up a little bit so you can see it better. Here down I still have f sub g. And I have two forces upwards. ft2 sine 30 and ft1 sine 60. And so now I've taken all of those forces and broken them into horizontal and vertical. Yep. Yep, every single one that has, yep. Well, sure, we can take to the left and down as negative, or we can take it as positive. It's up to you. Which one do you want? Do you want to do that for this one? Negative to the left and negative down? Okay, that's fine. I really don't have a preference, so I'm going to start on the x side here, and of course I only have the one equation in this whole section, and now I've got the sum of the forces in the x equals max. I know my a is 0 because all these are static or not accelerating. I'm going to have negative ft1 cosine 60 degrees plus ft2 cosine 30 degrees. I'm getting those right from my diagram above, and as Sarah pointed out, I'm taking the left to be negative and the right to be positive. That's how I know what sign they are. Equals m times 0. And so my next simplification step might be something like ft2 cosine 30 degrees equals ft1 cosine 60 degrees. But I can't really go any further there because I have ft2 that I don't know and ft1 that I don't know. So I'm kind of stuck on this side. I can't go any further. Yes, sir? No, m would be the mass of the traffic light. M mass. Or inertia. And actually, in this case, it would be the inertia. The mass only comes in cases of the weight. So, but whatever the inertia is, times 0 is going to give me 0. Right? On the y side, I have three forces, but I only have one equation. And so we're taking up as positive, ft1 sine of 60 degrees plus ft2 sine of 30 degrees minus f sub g equals m times 0 again. So most simplification I can do at this point, ft1 sine 60 degrees plus ft2 sine 30 degrees equals fg. And I remember from my equation sheet that fg is m little g. So I can substitute that in. I could write that rather than f sub g. The mass times little g. And so I'm kind of stuck on both sides. But I've got the same two unknowns on both sides. So I know algebraically I can solve it. Your choice at this point is to do it by hand or to use some type of solver. I would suggest doing it probably by hand. but you might want to use a solver. If you do use something like Wolfram or one of the other online solvers, I would suggest finding the values for cosine of 30 and sine of 60 and all those, not putting in the trig function. But, finding from your calculator that, like, I think sine of 30 is 0.5 or something like that. That's what I would suggest. I would, algebraically, the way you would do it is, since we have two equations with two unknowns, what I need to do is solve one of those equations for the other one, or for one of the variables, and then plug it into the other one. All right? So it looks to me like the easier one to solve for one of the variables is the green, is the x side. And we could solve it for ft2 or ft1. Which one do you want to solve? ft2? All right, so let's solve it for ft2. If I did that, I would have ft2 equals ft1 times cosine of 60 over cosine of 30. I kind of want to find out what that number is, so I'm going to actually find out what that number is by using my calculator. So I'll pull up my calculator, and I'm going to do cosine of 60 over cosine of 60, close parentheses, divided by cosine of 30, close parentheses, and I get that kind of nasty number, 0.57735. So I'm going to put that in 0.57735. Of course, I'll keep the real number in my calculator so I can just use it, so I don't have to otherwise write down all the digits if you don't have a calculator that will keep it. So now I can replace ft2 over on this side with that value. So I do that, ft1, might as well look up sine, might as well put in sine of 60. Let's see what sine of 60 is. Sine of 60 is 0.86602. 0.86602 plus ft1 times 0.57735. All that times sine of 30. Because sine of 30 is 0.5. Where do you see I did it twice? Oh, because see, I need to actually, I'm substituting in for ft2, this value that we found for it over here. And here I can't just drop an ft1. I have to keep the ones that are in the equation. I mean, if the ft1s and 2s are freaking you out because of their notation, replace them with x and y, a and b, George and Charlie, whatever makes sense to you. You know, there's no special things in the variables here. And I might as well substitute in for my mass, which in my case is 19.5. So 19.5, and my G is 9.80 newtons per kilogram. Sorry, just kind of ran out of space there. And now pulling things out, kind of organizing mathematically, ft1, that would be 0.86602 plus 0.57735 times 0.5. All that equals, again, 19.5 times 9.8. So 19, oops. 19.5 times 9.8. 191.1. 9.80 newtons per kilogram. And now I can find what FT1 is, because it's my only variable left in that whole expression. And so let's see, I'm going to do 19.91 divided by, parentheses, 0.866. I need to arrow up until I get that. 0.866 plus 0.577 times 0.5 parentheses, and I get 165. If I round to 3 sig figs, I get 165 newtons. That one. And then that's what I'm going to plug in over here to solve for FT2. Whatever that was, 165.497 newtons times 0.57735. So FT2. So that times 0.577. There it is. And I get 95.6. Let's see if that's correct. So my FT1 was on the left-hand side. Probably the last thing to be careful of. You want to make sure you put them into the right things. So like this, the left hand was my FT1, 165. Then my right-hand cable was my FT2, which is 95.6. See if I got it right. Yay. Always good on the All right. We're going to talk about number 2, about the slingshot. Wide rubber band, you practice hurdles and pebbles. Pull back to this force, and the angle between the two halves. What's the tension in the band? One way to simplify this one that will make life easier is to realize that if it's a single band, then it has a single tension in it. All right? Like in number 3 here, which we just did, the two cords are separate pieces of cord. That's how they can be at different angles. But if you have a single band, like here in number 2, or standing on a single wire or something like that, you have a tension in that item of the same value. And that can make your life simpler when you're solving. If you forget that, that's fine. You'll still be able to solve it, but you'll just find out that the tension in either band is the same. So I'm going to kind of draw looking down on our slingshot. So there's the post of our slingshot. Our band comes back like that, and our pebble would sit right in that kind of that mouth there of this. I pull backwards with a force. I've got a force of tension that pulls from either direction, and that I'm going to just label them F's of T because I have the same band. That's what I was just talking about, making my life simpler. Rather than having 2 tension, I have 1. And then they tell me that this angle in my case is 120 degrees, yours might be different. All right? So that would be, and I have no acceleration because I haven't let go of the pebble. You know, a problem we could do later would be what would be the acceleration of, you know, like a 5-gram pebble or something like that. That could be a problem on the next WebAssign set. But for this one, we have no acceleration, so we might even write in there, you know, acceleration equals 0 meters per second squared. That can help us remind ourselves of it. All right, and then for my free body of that same situation, got my dot. I'm going to have a force Ft in this direction, same force Ft in this direction, and my force F in that direction. And I want to break up my components here. So if I say if I've got an Ft that way and an Ft this way, if I'm to make those into triangles, these angles here would be 60 degrees since they have to add up to 120, and I'm kind of bisecting that angle. So that means I've got a component this way, both of them, and a component this way in both of them. This one for each of them is going to be Ft cosine 60, and each of these will be Ft sine of 60. Okay? Because I'm bisecting the angle and they need to add up to 120. So they're going to be different for you. What's your angle? So you're going to have to divide that by 2. Yeah. So what, 58.5, I think? So notice no gravitational force because that would actually, if we were to do the rocket, be in the other direction. So what I'm going to have is in the x direction in this one, 3 forces. So look at it, and in the y direction, I'm going to have just 2 forces in this case. So in my y direction, I've got a force up and a force down, Ft sine of 60 degrees, and Ft sine of 60 degrees. In my x, I've got that force that I'm applying backwards, F, or to the left, F. And I've got the 2 forces forward, Ft cosine 60 degrees and Ft cosine 60 degrees. Now, if you draw in your slingshot rather than sideways, up and down, the x and y would be swapped, which would be fine also. I'm not going to do anything on the y side because I'm looking at that and it says, okay, since there's no acceleration, that means those 2 forces have to balance each other. All I'm going to show over there is that Ft equals Ft. Because cosine of 60 is going to cancel out, which is great. That means that it's true that the tension is the same everywhere in the band, but I kind of assumed that at the beginning, so why go and prove it again? I hadn't, and I had labeled it like Ft1 and Ft2. I could prove that Ft1 and Ft2 are the same. That's what I can do on my y side. On my x side, I'm going to do my one equation, and I'm going to have, Sarah, do you want to take to the left as negative again? Okay. Negative F plus Ft cosine 60 degrees minus plus ft cosine 60 degrees equals 0. I got the 0 from the mass times the acceleration being 0. Yes, ma'am. No, because they're added. But what I can write is the next step I was going to write, which is 2 times ft cosine 60 degrees, and we'll put parentheses around it just to make more people happy, equals f. Right. Good. Yeah. So we have. I know that's what you. Someone listening at home though. And then if I rearrange this, I can have ft. It's f over 2 times cosine of 60 degrees. And now, first thing I'm going to put in my numbers. You could have put in your numbers a step before, or a couple steps before. My F, they tell me, is 2.34 newtons. So I have Ft for me. It is 2.34 newtons over 2 cosine 60 degrees. And so, do a little calculator work. 2.34 divided by parentheses 2 cosine 60. I have to make sure I use that parentheses in there. Keep our order of operations today. And I get 2.34. Oh, that's because cosine of 60, for me, is 0.5. 0.5 times 2 is 1. And anything divided by 1 is the number. So, let's try that. Alright, so we're looking at number 4 here. I'm going to grab those pictures so I don't have to redraw them. This is where part of that rubric of all needed diagrams comes into place, because where we have 2 situations here, we're going to need 2 force diagrams to start off and 2 free body diagrams probably to start off. So now, one thing we hadn't talked about is this thing up top that the rope goes around. Does anyone know the name of it? A pulley. And they tell us from a pulley and the tension rope is this block. So since they don't tell us that, like there's friction or anything like that, and we haven't learned about those on that pulley, we can kind of forget that it's even there. It's just a nice, what a pulley does is it changes the direction of force. So a force that was in this rope that was going upwards goes around this pulley, and now that force is going downwards. Or a pulley can change the direction of the force, make it sideways. So pulleys, basically, their main job is to change the direction of force. So I'm going to do my force diagrams here. This is problem number 4. I have F sub G down in both cases. Up here I have FT1. FT, let's call it FTA, since it's for drawing A. And here I only have FTB. Both of them, their accelerations are 0. So, I mean, we're going to go through the work, but intuition-wise, look at FTB, look at FTA. What tells you how they're going to compare? No? Well, I look at it and I say, oh, look, 2 FTAs add up to FG. and only one FTB adds up to FG. Let's see, if I had two numbers that had to add up to 10, and I had one number that had to add up to 10, oh, that one number is going to be 10. Now, what could those two numbers that are equal be that add up to 10? 5. So it's going to be, FTB is going to be twice as big as FTA? Maybe. Let's see. Maybe, maybe not. So, in situation A, I'm going to use this side for A and this side for B. So, drawing my free bodies in here, really in these, it's a lot of same type stuff. I can't remember if I used upper or lowercase, so. And those would be what my two free bodies should look like. And down here I'm going to continue using this side for A and this side for B, since everything is in the Y direction, I don't have to worry about X at all. And so I'll do the sum of my forces for A equals MA, and then the sum of my forces for B equals MAB. And for B, sir, are we going to take up as positive again? Okay. FTB minus FG equals M times 0. FTB equals FG. Over here, I've got FTA plus FTA, because both those are pointing upwards. And then downwards, I've got FG equals M times 0. So 2 times FTA equals FG. Right? They tell me FTA is 79 newtons in my case. So 2 times 79 newtons equals FG. And so FTB must equal 2 times 79 newtons, which is 158 newtons. Let's see if it's right.